Okay, hello everyone. Welcome back to Maps, Mapping, and Geospatial Technologies. Today's subject for week 7 is remote sensing, detecting energy from space. Remote sensing is a bit of a long topic. It could honestly probably be a course on its own, so do bear with me. This one will probably be a pretty long lecture. So what is remote sensing? Remote sensing is the observation and measurement of objects from a distance. For example, instruments or recorders are not in direct contact with objects under investigation. Remote sensing depends upon measuring some kind of energy that is emitted, transmitted, or reflected from an object in order to determine certain physical properties of the object. One of the most common types of remote sensing is photography. So kites and pigeons. In 1860, James W. Black took aerial photographs of Boston from a balloon above the city. However, development times, problems with landing at a prearranged location, and interference with the photographic plates from the balloon's gas all contributed to the view that balloons were not a practical platform for capturing aerial photographs. By the end of the 19th century, photographic equipment was being attached to kites and used to photograph the landscape remotely while the photographer was safely on the ground. A famous example of kite photography comes from 1906, when photographer George Lawrence used a set of kites 1,000 feet above San Francisco Bay to capture an aerial image of the city in the wake of the 1906 earthquake. During World War I, aerial photographs taken from airplanes were commonly used for map making and for planning military tactics. Aerial photography of battlefields allowed for the patterns of trenches to be determined, enemy positions to be observed, troop movements and encampments to be plotted, and the locations of artillery and supplies to be found. Countless aerial photos were shot and developed over the course of the war, opening up new possibilities in military intelligence. Post-World War II, aerial photography remained critical for military applications, especially for spy planes. In the 1950s, we saw the development of the U-2 spy plane, which was capable of flying at an altitude of 70,000 feet, traveling at over 400 miles an hour, and photographing the ground below. The U-2 was used for taking aerial photographs over the Soviet Union and was also enabled the acquisition of imagery showing the placement of missile launchers at key points in Cuba during the Cuban Missile Crisis in October 1962. So this is just the brief history, early experimentation with aerial photography, airborne remote sensing used during World War I and World War II from the hot air balloons, rudimentary spaceborne satellite remote sensing in the 1950s, meteorological satellite sensor remote sensing in the 1960s. Then we had the Landsat in 1972. European Space Agency launches the ERS-1 in 1991. MODIS and a couple of other different systems were launched to monitor pollution in 1999. Commercial satellites take the lead in 2000. And then high resolution and constellations can be photographed in 2008. And now we have microsatellites in the 2020s. As the name implies, UAS are not flown by a pilot in the cockpit. Instead, the pilot controls the UAS from the ground. UAS have been used for military operations to collect aerial imagery for reconnaissance, and they have been weaponized for both imaging and combat strikes. Today, commercial, public sector, and research uses UAS have become big business, and UAS are an integral part of the geospatial world. The equipment on board UAS collects remotely sensed aerial imagery and video, and UAS can be launched and used on demand as the user needs it for a variety of different applications. For instance, border patrols and port security offices use UAS for viewing areas remotely and getting a bird's eye view for increased monitoring and safety. Police forces use UAS for collecting imagery to aid in fighting crime and for increased reconnaissance of locations. Farmers utilize UAS to collect imagery to use for crop and irrigation monitoring. Researchers and universities own UAS and fly them for imagery data collection to aid in projects. Today, UAS are more affordable, and a multitude of companies, including firms such as 3DR, DJI, Parrot, SenseFly, and Unique, produce UAS that can be used for recreational research or commercial purposes. Civilian UAS range from drones that you can easily carry in one hand to larger, more robust models that can be purchased relatively inexpensively. Satellites travel at 17,000 miles per hour, which means in a given day, satellites can travel the entire circumference of the globe about 14 times. It would be like flying from Singapore to Los Angeles and back in 1 hour. Maxar's Earth observation satellites are designed to last 10 to 12 years on orbit. Additional factoids, the Maxar operates the most sophisticated Earth imaging constellation, which collects more than 3 million square kilometers of high-resolution satellite imagery each day. This daily collection is constantly feeding into the 100 plus petabyte data archive that also contains millions of square kilometers of imagery from our retired satellites, creating a digital time machine that allows you to analyze change dating back 20 years in very high resolution. So some fun facts. The satellite travels at 17,000 miles per hour. It gets better fuel economy than a Prius. Many satellites are powered by rechargeable batteries, taking advantage of the ultimate battery charger, that being the sun. Silvery solar panels are prominent features on many satellites. Other satellites have fuel cells that convert chemical energy to electrical energy, while a few rely on nuclear energy. The lifespan of a satellite is 10 to 12 years. The Earth observation satellites orbit about 383 miles above the Earth. That's the distance between Washington, D.C. and Boston. Or if you rotated the state of Florida, so it was standing up, that's how high up the satellites orbit. Many remote sensing satellites operate in near polar orbit, a north to south path wherein the satellite moves close to the North Pole and South Poles as it makes several passes a day about Earth. While a satellite in continuous orbit passes over Earth, it is imaging the ground below. However, during an orbit, a satellite can image only a certain area of ground at a time. It can't see everything at once. The swath width is a measurement of the width of ground the satellite can image during one pass. A Landsat satellite's sensor has a swath width of 185 kilometers, meaning that a 185 kilometer wide area on the ground is imaged as Landsat flies overhead. A satellite's orbit Earth is rotating beneath them, and several days many elapse before an orbital path thus the swath of ground being imaged. This takes a satellite over nearby geographic areas. For example, a Landsat satellite may pass over the middle of the United States on day 1 of its orbit, pass hundreds of miles to the west on day 2, and may not return to the path next to the first one until day 8. A sun synchronous orbit occurs when a satellite's orbit always takes over the same swath of Earth's surface at the same local time. As a result, images collected from such a satellite will have similar sun lighting conditions and can be used to compare changes to an area over time. For instance, Landsat 8 has a sun-synchronous orbit, allowing it to cross the equator at the same time every day. Satellites onboard sensors have different ways of scanning the ground and collecting information on the swath being imaged. In a long track scanning, a linear array scans the ground along the satellite's orbital path as the satellite moves. The detectors in the array collect information from the entire swath width below them. This type of sensor is referred to as a push broom. Think of pushing a broom in a straight line across a floor, but in this case the broom is the sensor and each bristle of the broom represents a part of the array that senses what is on the ground below it. A second method is across track scanning. Here, a rotating mirror moves back and forth over the swath width of the ground to collect information. This type of sensor is referred to as whisk broom. After a satellite's sensors have collected data, the data needs to be offloaded from the satellite and sent to Earth. Because data collection is continuous, this information needs to get to people on the surface so that it can be processed and utilized as it becomes available. The Earth Resources Observation and Science, or EROS, Center, located outside of Sioux Falls, South Dakota, is one of the downlink stations in the United States that receives data from numerous remote sensing satellites. Satellite data can be sent directly to a receiver at a station or transmitted to other tracking and data relay satellites, which then send the data to Earth. Once received on the ground, the data can be processed into imagery. So there are a couple different types of sensors. There's passive sensors, which measure naturally occurring radiation. Active sensors, which emit their own radiation and measure the reflection. Passive sensors have two main shortcomings. Cloud cover blocks these wavelengths and they're only measurable in daylight. Active sensors use long-wave radiation, for example microwaves, that can penetrate clouds, but the objects on the surface of Earth do not emit enough microwaves to be easily detectable from space. These techniques are based on sensing electromagnetic energy emitted or reflected from the Earth's surface and detected at some altitude above the ground. The electromagnetic spectrum is then the starting point for understanding remote sensing. Passive remote sensing is based on detecting available electromagnetic energy from natural sources such as sunlight, and active remote sensing, in contrast, depends on an artificial light source such as radar to illuminate the scene. So if remote sensing measures the reflectance of electromagnetic energy, there needs to be a source for that energy. Luckily, we have one somewhat nearby, that being the sun. Sun is almost 93 million miles away from Earth, and the sunlight takes about 8.3 minutes to reach Earth. This solar energy radiates through space at the speed of light, almost 300 million meters per second, and it passes through and interacts with Earth's atmosphere before it reaches Earth's surface. The energy then interacts with objects on Earth's surface, and some of the energy is reflected back into space. That reflected energy passes back through the atmosphere and can be picked up and recorded by sensors on airborne and spaceborne platforms. The sun produces all sorts of energy: ultraviolet light, visible light, infrared light, and more. And although the human eye can only see a very small portion of this energy, remote sensing devices can potentially see all of these types of energy. In addition to the kinds of energy that people can see, it's these invisible to the human eye types of energies that become very important in remote sensing. Incident energy is the total amount of energy per wavelength that interacts with an object. Transmission occurs when a wavelength of energy simply passes through a surface to interact with something else for later. For example, when light passes through the windshield of a car, most of the light passes through the glass to affect things in the car rather than to affect the windshield itself. Then there is absorption, which occurs when energy is trapped and held by a surface rather than passing through or reflecting off of it. Think of walking across a blacktop parking lot during a hot summer day. If you don't have something on your feet, you're going to hurt them from the heat on the pavement. So what is electromagnetic energy? One technique that can be used for teaching this between the difference between wavelength and frequency, or the connection between wavelength and frequency, is to liken it to the students sitting on a beach and watching the ocean waves come into the shore. When the ocean is calm, the waves show up less frequently, and so there's a greater length between the waves. The ocean is choppy and waves show up more frequently, so there's a shorter length between waves. Using that analogy, we then move into how waves of energy radiate from the sun and discuss how wavelength times frequency has to equal a constant value, or c. C being the speed of light. In this case, a high frequency needs to be balanced out by a shorter wavelength, while a low frequency must be balanced out by a longer wavelength. A wavelength is a distance between the crests of two waves. Therefore, the longer the wavelength, you see the further. With a longer wavelength, you see waves far less frequently, and with a shorter wavelength, you see waves a lot more frequently. Electromagnetic energy at different wavelengths also has different properties. Light energy with very long wavelengths has different characteristics from light that has a very short wavelengths. The electromagnetic spectrum is used to examine the properties of light energy in relation to wavelength. The values of the wavelengths are usually measured in extremely small units of measurement called micrometers. A micrometer is 1/1,000,000th of a meter, roughly the thickness of a single bacterium. Sometimes an even smaller unit of measurement called a nanometer can be used. A nanometer is 1/1000,000th of a meter. Forms of electromagnetic energy with very short wavelengths are cosmic rays, gamma rays, and X-rays, while forms of electromagnetic energy with long wavelengths are microwaves and radio waves. It's important to remember that the sun radiates many types of energy, but they're invisible to the human eye. When you put a slice of cold pizza in the microwave oven to heat it, you don't actually see the microwaves bombarding the pizza to heat it up. Similarly, you can't see the X-rays that a doctor uses in an exam, or the radio waves that are picked up by your car's antenna. All this energy is out there, and you just can't see it. This is because of our eyes, which are structured to respond to reflected light. and are sensitive only to the reflective light that has a wavelength between 0.4 and 0.7 micrometers. This portion of the electromagnetic spectrum is called the visible light spectrum. Each of these narrow portions of the electromagnetic spectrum that present a particular form of light is referred to as a band of energy in remote sensing. For example, the shorter wavelengths of 0.4 to 0.5 micrometers are referred to as the blue band of the electromagnetic spectrum because the properties of those wavelengths of light correspond to the characteristics of blue energy. Wavelengths between 0.5 and 0.6 micrometers make up the green band of electromagnetic spectrum. The wavelengths between 0.6 and 0.7 micrometers make up the red band. The wavelengths of energy that pass through our atmosphere are referred to as atmospheric windows. That's why we set up sensors in those specific windows where light is being reflected back and not absorbed by the atmosphere. While some light energy is absorbed by the atmosphere, other light energy is scattered by it. Scattering is caused by particles such as dust and water in the atmosphere. It is always present, but its effects are always unpredictable. Light hitting these particles is absorbed and redirected back out in random directions, causing the scattering. The first of these is Rayleigh scattering, which occurs when the particles causing scattering are significantly smaller than the wavelengths being affected. Keeping in mind that the visible light wavelengths are smaller than 1/1,000,000th of a meter, Rayleigh scattering is caused by molecules in the atmosphere. In addition, shorter wavelengths are scattered to a much greater degree than longer wavelengths. This explains why the sky is blue during the day. The shorter blue wavelengths are scattered far more than the longer red wavelengths. However, at sunset and sunrise, sunlight has a longer distance to travel to reach the Earth, and thus, with all the blue wavelengths already scattered, we see the reds and oranges of longer wavelengths as the sun goes down out of view. So, how do we visualize this data? Raster data, where each pixel received a digital number or a brightness value for the amount of radiance being measured at the sensor for that section of the ground. Low means it has less radiance or it is darker. Digital numbers are scaled to fit a range by the sensor. 8-bit imagery is scaled from values of 0 to 255 in grayscale, known as panchromatic. It treats the entire visible spectrum as if it were one band. Color imagery captures the three main bands of visible light, red, green, and blue, and the colors are composited together in the digital imagery or film as a true color composite. Uses 3 channels, red, green, and blue, because you can create up to 6,777,216 color combinations if you consider 0 to 255 pixel values for each of the primary colors. A color infrared photo, or CIR photo, is a distinctive type of aerial color photo. A CIR image is captured with a special type of film that's sensitive to infrared light. Infrared energy is invisible to the naked eye, but special film processes can capture it. To enable humans to see infrared energy reflection, a special filter is applied to the film, and the end result is a CIR photo, wherein near-infrared NIR or NIR reflection is displayed in the color red. Red reflection is displayed in the color green. Blue reflection is not shown in the image as it is blocked by the filter and displayed as black. In the following example, the RGB image shows shades of green that are more subtle and structures are significantly less distinct, whereas the CIR image clearly shows different shades of red for dense canopy and other vegetation species, while structures and roads appear blue-green. For many applications, particularly those involving vegetation and wetlands, the fourth band in the aerial imagery product provides a wealth of information. The fourth band refers to the near-infrared wavelength in the electromagnetic spectrum, invisible to the human eye, but a valuable tool for image analysis and change detection. A color infrared or false color image is composed of near-infrared wavelengths, red and green bands, while a true color image displays the visible red, green, and blue bands. By displaying the invisible NIR bands as a visible band, the NIR reflectance values can be seen and analyzed. Color infrared valuable for vegetation analysis. In a CIR image, the internal cell structure of vegetation strongly reflects the NIR wavelength and provides a more robust indicator of plant health, and a visible green wavelength reflection of chlorophyll in the leaves. On your computer, the NIR band is typically displayed as red for easy identification, and different shades of red color show varying levels of plant health and vigor. A healthy plant is bright red, while dead, dormant, or unhealthy plants are lighter shades of red or blue-green. At the same time, water absorbs the NIR wavelength, so it appears black in a CIR image. Therefore, CIR images are used to access the turbidity or quality of water. Sediment and suspended particles in water are detected by the NIR wavelength and are seen as shades of blue instead of black. What to look for in color infrared photographs, keeping in mind that vegetation absorbs the red and NIR wavelengths at a higher percentage than blue and green wavelengths. The human eye and computer recognition technology can distinguish variations in vegetation more easily than a CIR image, which makes them ideal for analysis. The next example shows a contrast in vegetation health as well as diverse plant species. I don't know if there is a next example. Okay, so cut it at 30 minutes. Okay. The various objects that make up the surface absorb and reflect different amounts of energy at different wavelengths. The magnitude of energy that an object reflects or emits across a range of wavelengths is called a spectral response pattern. Like most vegetation, the chlorophyll in grass absorbs visible energy, particularly in the blue and red wavelengths for use during photosynthesis. About half of the incoming near-infrared radiation is reflected, however, which is characteristic of healthy, hydrated vegetation. Brownish-gray soil reflects more energy at a longer wavelengths than grass. Water absorbs more incoming radiation across the entire range of wavelengths. Knowing their typical spectral response characteristics, it is possible to identify forests, crops, soils, and geological formations in remotely sensed imagery and to evaluate their condition. So why is this important? The various objects that make up the surface absorb and reflect different amounts of energy at different wavelengths. The magnitude of energy that an object reflects or emits across a range of wavelengths is called a spectral response pattern. Like most vegetation, the chlorophyll in grass absorbs visible energy, particularly in the blue and red wavelengths, for use during photosynthesis. About half of the incoming near-infrared radiation is reflected, however, which is characteristic of healthy hydrated vegetation. Brownish gray soil is the exact same. So spectral signature, the spectral reflectance is the percent of the total wavelength reflected back to a sensor, and it is a unique identifier for a particularly item based against the spectral reflectance. So what makes all of this important? The various objects that make up the surface absorb and reflect different amounts of energy at different wavelengths. Magnitude of energy that an object reflects or emits across a range of wavelengths is called a spectral response pattern, as I just talked about on the last slide. Like most vegetation, the chlorophyll in grass absorbs visible energy, particularly the blue and red wavelengths, for use during photosynthesis. About half of the incoming near-infrared radiation is reflected, however, which is characteristics of healthy hydrated vegetation. Brownish gray soil reflects more energy at longer wavelengths in grass. Water absorbs most incoming radiation across the entire range of wavelengths. Knowing their typical spectral response characteristics, it is possible to identify forests, crops, soils, and geological formations in remotely sensed imagery and evaluate their condition. Normalized Difference Vegetation Index, which is derived from remote sensing satellite data, is closely linked to drought conditions. To determine the density of green on a patch of land, the distinct colors of visible and near-infrared sunlight reflected by the plants are observed. The range is NDVI. The range of NDVI is -1 to +1. Higher value of NDVI refers to healthy and dense vegetation. Lower NDVI values show sparse vegetation. In the example on the screen, where NDVI equals NIR minus red over NIR plus red, the NIR stands for the spectral reflectance, which is measurements acquired in the red and near-infrared regions, respectively. Remember, healthy vegetation reflects more near-infrared and green light compared to other wavelengths, but it absorbs more red and blue light, and that's why we see our vegetation as green. Here are a couple of examples. So what is the solution? There is the temporal resolution, which refers to how often the sensor can return to image the same spot on Earth's surface. For instance, a sensor with 16-day temporal resolution would collect information about the swath containing your house and would not return to image it again until 16 days had passed. The finer a sensor's temporal resolution, the fewer days between return times. The time factor in imaging is important when we consider persistent clouds offer limited clear views of the Earth's surface, short-lived phenomenon such as floods, oil slicks, and more would need to be imaged. Multi-temporal comparisons are required. For example, the spread of a forest disease from one year to the next. And lastly, the changing appearance of a feature over time can be used to distinguish it from near similar features such as wheat or maize. A way to improve a sensor's temporal resolution is to use off-nadir viewing capability, which is the sensor in which the sensor is not fixed to sense what's directly below it. A sensor that is capable of viewing places off-nadir can be pointed to image locations away from the orbital path. Using off-nadir viewing can greatly increase a sensor's temporal resolution, as the sensor can image a target several times during its orbit, even if the satellite isn't directly overhead. This capability is a great help in monitoring conditions that can change quickly or that require rapid responses, such as mitigating disasters resulting from hurricanes, tornadoes, or wildfires. Radiometric resolution. As mentioned in Chapter 10, a sensor scales the energy measurements into several different ranges to assign brightness values to a pixel. The sensor's radiometric resolution refers to its ability to measure fine differences in energy. For instance, a sensor with 8-bit radiometric resolution places the energy radiance values on a scale of 0 to 255, 0 being the lowest radiance and 255 being the highest. The wider the range of measurements that can be made, the finer the sensor's radiometric resolution. The radiometric resolution is a measure of the sensor's bits of precision. The finer a sensor's radiometric resolution, the better it can discriminate between smaller differences in energy measurements. To calculate the numbers of levels, you apply the number of bits to an exponent to the number of 2. For instance, a 6-bit sensor would have 64 levels, ranging from a value of 0 to a value of 63. An 8-bit sensor would have 256 levels, ranging from 0 to 255. An 11-bit sensor would have 2048 levels, ranging from 0 to 2047. Sensor's parameter is its spectral resolution, which refers to the bands of their wavelengths measured by the sensor. For instance, a sensor on the GeoEye-1 satellite can measure 4 bands of energy simultaneously, and the sensor on board the Landsat 8 satellite can sense 7 different wavelengths at the same time. A sensor with a higher spectral resolution can examine several finer intervals of energy wavelengths. For example, the MODIS sensor on board the Terra satellite can sense in 36 different bands at once. Being able to sense numerous smaller wavelengths in the near-infrared portion of the spectrum gives much finer spectral resolution than just sensing one wider wavelength of near-infrared energy. A sensor is defined based on the bands it can measure. A panchromatic sensor measures one wide range of wavelengths, usually the entire visible portion as one band, or sometimes the visible portion and part of the infrared spectrum as one single band. This produces black, white, and grayscale panchromatic imagery. A multispectral sensor measures several bands of energy. For instance, the MODIS sensor mentioned earlier in this chapter is an example of a multispectral sensor. that measures 36 different bands and produces multispectral imagery. A hyperspectral sensor is capable of sensing hundreds of very fine band wavelengths at once and produces hyperspectral imagery. Spatial resolution, with the area on the ground represented by 1 pixel in a satellite image. The sensor's spatial resolution affects the amount of detail that can be determined from the imagery. For example, a sensor with a 1 meter spatial resolution has a much finer resolution than a sensor with a spatial resolution of 30 meters. Smaller cell size equals higher resolution, higher spatial accuracy, slower display/processing, and larger file size. If two bands, one with a higher resolution than the other, are used by a sensor to image the same area, the higher resolution band can be used to sharpen the resolution of the lower resolution band. This technique is referred to as pan sharpening because the higher resolution band used is a panchromatic band acquired by a panchromatic sensor. For example, a satellite like the Landsat 8 that uses the blue, green, and red portions of the electromagnetic spectrum at 30-meter resolution could have a sensor equipped to view the entire visible portion of the spectrum and part of the near-infrared spectrum as a panchromatic band at 15-meter resolution. This panchromatic image can be fused with the other 30-meter resolution color imagery to create a higher resolution color composite. Many satellites with higher spatial resolution capabilities sense in a panchromatic band that allows for pan sharpening of the imagery in the other bands. Here's an example of Maxar's industry-leading resolution and how it can deliver clear insight to a time of crisis. Again, this is Greensburg, Kansas City tornado imagery. Here's resolution at 1 meter, high enough resolution, for example, to define areas of impact. Here is Greensburg at a 0.82 meter or 82 centimeters, which is the resolution at IKONOS satellite collects. Here it is at 50 centimeters or half a meter. We're able to get out more detail related to assessing property damage or documenting losses. Here it is at 41 centimeters, which is the resolution at GeoEye-1 collects. And here we are at 31 centimeters, which is the resolution that Worldview 3 collects. What would eventually become of the U.S. Landsat program was conceived in the late 1960s as a resource for doing remote sensing of Earth from space. The program's first satellite, Landsat 1, was launched in 1972, and the program continues on today. Most recent launch was the Landsat 9, and it occurred in 2021. Landsat 1 sensor was the Landsat MSS multispectral scanner, which had a temporal resolution of 18 days. The MSS, which continued to be part of the Landsat missions through Landsat 5, was capable of sensing 4 bands, red and green, plus 2 bands in the near infrared, at 79-meter spatial resolution and a 6-bit radiometric resolution. As the name implies, MSS is an example of a multispectral sensor, which can measure multiple wavelengths at once. In addition to using the MSS, Landsats 4 and 5 were also equipped with a new remote sensing device called the TM, or Thematic Mapper. The TM was another multispectral sensor that allowed for sensing in 7 bands in the electromagnetic spectrum simultaneously, including the 3 visible bands, a band of NIR, 2 bands of SWIR, and a thermal band. The TM bands had improved radiometric resolution over MSS of 8 bits, and the spatial resolution of the multispectral bands was improved to 30 meters. The swath width was 185 kilometers. TM also had an improved temporal resolution of 16 days. Landsat 7, launched in 1999, carries neither the MSS nor the TM. Instead, it carries a sensor called the ETM, or Enhanced Thematic Mapper Plus. This device senses the same 7 bands of their wavelengths as TM at the same swath width, as well as the same radiometric and spatial resolutions, although the thermal band's spatial resolution has been improved to 60 meters. It also includes a new band 8, which is a panchromatic band covering wavelengths of 0.52 through 0.9 micrometers with a spatial resolution of 15 meters. With this improved spatial resolution, the panchromatic band can be used to sharpen the quality of the other imagery. Landsat 7's temporal resolution is still 16 days, but it can collect about 475 images per day. Landsat 8 currently collects up to 740 images per day in its instruments over the 185 kilometer swath. Like Landsat 7, Landsat 8 has a 16-day temporal resolution. However, by having both Landsat 7 and 8 on the job, one of the 2 satellites can obtain an image of anywhere on the globe 8 days after the other. Landsat 8's sensor is the next iteration of Landsat technology. It is called OLI, Operational Land Imager, and it has capabilities similar to those of ETM+. OLI senses visible and infrared bands at 30 meter resolution, a panchromatic band at 15 meter resolution, and 2 new 30 meter bands aimed at monitoring clouds and coastal zones. A thermal band is not part of OLI, instead a separate instrument on the satellite called TIRS, Thermal Infrared Sensor, which collects 2 different bands of thermal data listed as bands 10 and 11 for Landsat 8. This thermal data is acquired at 100 meter resolution, but is then resampled to 30 meter resolution when delivered to users. Space is hard. For instance, a Landsat satellite has a prime technology life of 5 years, but can often continue to be used far beyond that time span. Landsat 5 was launched in 1984, and its successor, Landsat 6, was not launched until 1993. However, Landsat 6 failed to achieve orbit at launch and crashed into the Indian Ocean, where it is lost. The Landsat 5 mission therefore needed to continue until the launch of Landsat 7 in 1999. Imagery created by sensing multiple bands together is referred to as multispectral imagery. Some technology can simultaneously sense over 200 bands of the electromagnetic spectrum, producing hyperspectral imagery. In 2008, Landsat imagery was made free to public by USG, otherwise it would cost $4,000. Natural color composite image consists of blue, green, and red visible light portrayed in a natural manner. Active vegetation appears green, bare soil and fallow fields are brown, and urban structures are white. Clean water bodies appear black, whereas the Missouri River displays a muddy brown. Landsat TM bands 1, 2, and 3 are covered in this image. Standard false color composite. Image consists of green, red, and near-infrared light portrayed in a false color manner. Active vegetation appears red, pink, bare soil and fallow fields are green, and urban structures are bluish white. Clean water bodies appear black, whereas the Missouri River displays a green-brown color. Special color composite. This image consists of red, near-infrared, and mid-infrared light portrayed in a false color manner. Active vegetation appears green, bare soil and fallow fields are red, brown, and urban structures are purple. Most water bodies are black, and the Missouri River appears a dark blue. Vegetation image based on red and near-infrared bands. Active vegetation is green, dormant and dry plants are yellow. Plowed fields, pavement, and bare ground are brown. All water bodies appear to be black. And Landsat TM bands 3 and 4 are utilized to create the normalized difference vegetation index. So this is a hands-on activity for you guys to do. It does not appear to work anymore, so I apologize for that for anyone who was interested in checking it out. And then this is a video that I will play. So this is an application or website that allows you guys to go through and look at the different satellites and what sorts of images they are capturing. So unfortunately, I believe this is the hands-on activity. I got it from Josh Siskind. So I believe it's no longer available, unfortunately. There might be a new one, but this is the one I currently have. So yeah, this lets you go through and change what satellites you're looking at and what sorts of wavelengths and colors you can actually see of different areas on the ground. I think this is the exact same video, so this slide might be duplicated. So these images show how band combinations can be used to alter an image's appearance. A multispectral image takes data from specific light wavelengths from the electromagnetic spectrum or bands. Different combinations can be used for different purposes. Panchromatic images are displaying all colors in one channel instead of separately, and it is typically shown in a gray scale, also called black and white. Panchromatic images can be sharper because the sensor can see more light at once. The second image is natural color, or what the humans see. A green tree will be green and a blue ocean will be blue. Third image is in short wave infrared, SWIR, which is a subdivision along the infrared wavelength. Short wave infrared is good for determining many things, like where there is moisture, where fire is burning, and what materials are in the image. As you move from left to right on this slide, you can get an increasing amount of information. In the panchromatic image, you can see there's mountains. In the color image, you can see that the rocks making up the mountains are different. In the SWIR image, you can differentiate between the types of rocks. Different band combinations can be used to identify different features on the ground. Bands can be combined to create color pictures that highlight specific features, as shown in the following examples. SWIR bands are different from visible light bands because they can see through smoke. Using certain SWIR bands combinations allows firefighters to figure out where a fire is burning because it will highlight heat as red and yellow while emitting smoke and haze. This image is from Adelaide, Australia during the January 2015 fires. While we're focusing on satellites, can be from planes and UAVs. A synoptic view, satellites images are big picture views of large areas of the surface. The positions, distribution, and spatial relationships of features are clearly evident. Mega patterns within landscapes, seascapes, and icescapes are emphasized. Major biological, tectonic, hydraulic, and geomorphic factors stand out distinctively. Repetitive coverage, repeated images of the same regions taken at regular intervals over periods of days, years, and decades provide databases for recognizing and measuring environmental change. This is crucial for understanding where, when, and how the modern environment is changing. Multispectral data. Satellite sensors are designed to operate in many different portions of the electromagnetic spectrum. Ultraviolet, visible, infrared, and microwave energy coming from the Earth's surface or atmosphere contain a wealth of information about material composition and physical conditions. Low-cost data, near global repetitive collection of data is far cheaper using satellite sensors than collecting the same type of quantity of data would be through conventional ground surveys. So that is it. That is the entire lecture. I know this one was a bit of a long one, so hopefully I was able to keep your guys' attention. So just a couple of reminders. The quiz is due this coming Wednesday on the 26th, so make sure you get that in. Again, there will be no late submissions accepted. So just make sure you get it in. If you have questions, feel free to reach out to me. I will be available for office hours tomorrow and Wednesday if you need any help. Additionally, I did post the extra credit opportunity. You unfortunately will not be able to start it until I want to say it's March 11th. It's basically Esri is hosting a conference. It's called Developer Summit. It's hosted every year in the second week of March. I will be attending. I will actually be presenting multiple times during it. So all you guys have to do is register, create an account, and watch the Dev Summit Plenary, either day 1 or day 2. I think I'm presenting day 2 if you want to see some of the stuff I work on. Either day 1 or 2 will work. I'll make sure to update the document accordingly. and then just give a brief write-up afterwards, and it'll count for extra credit. So with that said, I'm going to leave you guys with all of this information I just dumped on you. So again, if you have any questions, please feel free to reach out. So yeah, have a good week, everyone.